Good morning, everyone. OK, this works. Cool. I'm Tim Beiko. I work at the Ethereum Foundation, and I'm here to give you a quick update of the Ethereum roadmap. Yeah. So first thing on the roadmap, you've probably heard about it, is the merge. So I'm going to walk you through what the merge actually is, where we are in the process, and what's left to do. And to do this, it's worth looking at like the Ethereum 2.0 roadmap that we publicized extensively several years ago, and how what we have today is kind of changed from that. So if you remember, like around 2018, 2019, there was this idea that Ethereum 2.0 would come in 3 phases. So there was phase 0, phase 1, phase 2. And it would be kind of sequential upgrades that get us to a fully scalable Ethereum running on proof of stake. And the first part of that, phase 0, was the beacon chain. So the beacon chain is the part of Ethereum that runs the proof of stake algorithm. And that launched in late 2020. After that, the plan was to create what we call data shards, which would store a bunch of data for Ethereum. And then the last part of the plan was something called execution environments, which would convert these shards which store data to basically EVM chains which run computation. And that was always the most complicated part of the plan. It was always something that kind of sounded good that we would do, but there was never like a great spec for how to get there. And so in parallel to launching the beacon chain, we started to see rollups develop and gain adoption. So rollups are basically a different way to scale Ethereum, where instead of having everything kind of live in the protocol, these rollups use layer 1 as a sort of anchor and source of security, but then create their own EVM or zero-knowledge computation environment where they run the transactions. And because this basically happened in parallel to us trying to deliver on this roadmap, it just made sense at some point to, instead of trying to do this really complicated phase 2 part of the plan, rely on rollups as the main way to scale Ethereum. And so we had kind of this rollup-centric roadmap in the middle, you can see, and the idea was like, well, we're going to have the beacon chain, we're going to have a single EVM chain, and then we're going to have the rollup scale execution. And then there was like a final insight that led to the current architecture we had, which is that today on Ethereum, the clients that run the Ethereum software, they can already run more than one consensus algorithm. So if you run a node on mainnet using Nethermine, Besu, Geth, you run under proof of work, obviously. But if you run on any of the testnets, you already run on a different algorithm. So none of the Ethereum testnets use proof of work. And so the idea that we had was, well, if these clients are already built in a way that they can use a different consensus mechanism, can we just have them use proof of stake instead and use the beacon chain as a source of consensus? And so that's what we came up with. And this is kind of what the current post-merge architecture for Ethereum will look like. So if you look on this slide, an Ethereum client, after the merge, basically becomes the combination of both a beacon node and an execution engine. And we call the beacon node and the general proof of stake chain the consensus layer of Ethereum, because it is what kind of provides consensus on the latest state of the chain. And the execution engine is basically what is known today as an ETH1 client. So you can think of something like Geth or Besu or something like that. And so after the merge, basically a full node will run the combination of both these things. So you'll have a consensus layer client, so something like Prism, Lighthouse, Lodestar, which talks to an execution engine, which is Geth or Besu or Aragon. And to make this work, we introduced a new communication API between both layers called the Engine API. But aside from that, things are pretty much unchanged from a network perspective. So that means that like, if you're an application and you use JSON RPC to interact with Geth, all of that is still going to work as it currently does. Or say you're like a block explorer and you're using the beacon APIs, all of these will keep working as is. And so what is great about this is like, we're reusing all of the software that's currently battle tested on mainnet and the beacon chain, keeping the user experience kind of the same. And from a smart contracts point of view, the merge is going to happen with basically no downtime. And if we zoom in a little bit, this is kind of what a post-merge block will look like. So at the outer, kind of the outer part here, the consensus layer, this is what's on the beacon chain today. So the beacon chain comes to consensus on blocks, but they only have this outer parts. They don't have this execution layer bit. So for example, every block in the beacon chain tells you what's the slot number, what's the parent root, there's a signature from the validator, there's all the attestations, all the new deposits, all the validator exits. But aside from that, it's empty. And today, we have kind of this execution layer, which contains all of like the transactions on Ethereum. So if you send a transaction, if a smart contract makes a transaction, all of that is included there. And there's also some other important information for execution, like the base fee and things like that. But today, this kind of execution blob has a proof of work layer around it. So after the merge, you basically combine these two and get this. So not a lot changes, actually. So the few things that are worth noting is the block times go from being about 13 seconds, but having a lot of variance because of proof of work, to always being 12 seconds, or a multiple if a validator is offline when they need to produce a block. There's a couple fields that we set to 0 in the blocks just because they don't matter anymore, anything related to proof of work. The one thing we don't set to 0, though, is the difficulty opcode. So if you're a smart contract developer, you'll know there's a way to get the difficulty opcode in Ethereum, and it's like a source of bad randomness, but anybody who uses it on chain basically uses it for pseudo-randomness. And if we set this to 0, it would go from being bad randomness to pretty terrible randomness. So instead, we return the random value from the beacon chain. And so how do we get from like the current proof of work system to the post-merge architecture? There's a couple steps. The first thing to note is that unlike previous upgrades on Ethereum, we're not using a block number for this. There's basically security considerations around that for how miners can fake chains with a large block number. So instead, what we use is the total difficulty of the proof of work. And just to give a quick overview of how that works, proof of work, basically, there's a difficulty to mine every block. If you add the difficulty of every block that's ever been mined in the chain, you get a total difficulty value. And so what we do to trigger the merge is we set a total difficulty value, which we call the terminal total difficulty. And once a block hits or exceeds that terminal total difficulty, we consider this to be the last proof of work block on the network. And so once we see a block that meets this condition, we then rely on the validator on the beacon chain who's set to produce the next block to simply include transactions as part of their block. And from that point, you basically have the last proof of work block, which exceeds the TTD. Then the next block is produced by a validator on the beacon chain, and we're not using proof of work anymore. And then the last thing we'll want to see after the merge is once we've had this first block produced by proof of stake, we want to see this finalized on the proof of stake side. And finalization is basically the proof of work equivalent of having a high number of confirmations where you have a high degree of certainty that the chain is not going to be reorged, and so you can consider like the first post-merge block to be final. So I know this is a lot, but I have a diagram to walk you through it. So bear with me, please. Okay. So this diagram basically shows what happens before and after the merge. So if you start way to the left on the top side, you have a proof of work block, like we saw earlier. So there's some proof of work stuff. We didn't include it. And then within that proof of work block, you have all of the execution layer content. So the parent hash of the block, the state root, the base fee, and the list of all the transactions included in that block. In parallel to that, we have the beacon chain running. So if you go right under that block, you can see there's a beacon chain block, which has all of this proof of stake information, but no transactions. If you forward kind of one step in the process, this would be kind of our final proof of work block. So if we had set the TTD would have been like crossed between the first two proof of work blocks. And that kind of triggers the merge. So at that time, we see there's like the last block on the beacon chain without any transactions. And then the merge basically happens. So the next block on the beacon chain simply has transactions included as part of it. The validator kind of run those, make sure that they're secure, that they're valid, and then references kind of the transactional content of the last proof of work block. But then after that one, you can see that the next block on the proof of stake side literally has no reference to proof of work. So from that point, we're running 100% under proof of stake. And so again, from like the perspective of a smart contract or anyone using the chain, you literally have kind of just two blocks coming. The last one's on proof of work, the next one's on proof of stake, and there's about 12 seconds between them, but there's not like a major delay or anything. So how do we actually ship this thing? So I'll walk you through like what we've been doing and kind of what we hope to do next. So earlier in the talk, I kind of showed how we got to this roadmap of using kind of both the execution layer, ConsenSys layer, having the engine API. So we got this idea kind of about a year ago, and in May of last year, we decided to actually prototype this with all the client teams to check if it would work. So we spent a month getting your first prototype, and we managed to get it working. So at that point, all we had was like a post-merge network. It didn't run through the merge or anything, but we were able to say that like this idea of having the validators run like a get node and produce and execute transactions in that and test that they're correct, we were able to confirm that that would work. Then we obviously had a ton of bugs in that, spent the summer debugging everything. In the fall, we were ready for kind of another round of prototyping. So we got all of the client teams together for a week, and we prototyped a network which started on proof of work and ran through the actual transition and ended up on proof of stake. So after that week, we kind of had high confidence that we could actually run through the process on an existing proof of stake network, and it would work. Again, tons of bugs we found, spent the next 2 months fixing them. Right before the holidays, we launched a first new testnet called Kintsugi, and the idea there is we were at a spot where we thought the spec was pretty final, and we wanted to get some early feedback from applications and users to see, does this make sense? Is there anything that's breaking? Obviously, some things broke, and we fixed them. And just a month ago, we launched Kiln, which we hope to be our last new testnet for the merge. So the idea with Kiln was that we found all these issues with Kintsugi, a bunch of edge cases in the spec, fixed them, but now we don't expect to make any major changes to how the merge is specified. Since we've launched Kiln, it's been about a month, we've started to find bugs basically in the client implementations. And the difference here is that the bugs we found on Kintsugi basically were telling us like the approach we're using for doing the merge has issues, whereas now the bugs we're finding tells us that one of the teams who implemented the specification kind of had an issue with how they did it. So over time, we're getting to more and more stable things and finding issues farther and farther up the stack, which is a promising sign. The next thing that we started doing, and that's what we've been doing extensively in the past month, is called shadow forks. So this is a new thing we've added as part of our testing cycle, which is extremely helpful. So what we do is we take an existing network, something like Goerli or even mainnet, and we launch a small number of nodes on it, which actually run through the merge. So you can think of it like a hard fork, but there's only like a tiny number of people who are running the nodes going through the hard fork. So the rest of the network kind of has no idea this is happening, but in parallel, we've run through this hard fork and kind of see if it works. And the thing that's really useful there is that once we actually upgrade to the merge, we can still replay the transactions from the main network on our shadow fork. So it gets you to test this in an environment that's basically the same as either Goerli or mainnet, which helps us uncover issues that we would otherwise find on those networks. So basically how we get to mainnet. So on the first side here is how we'll get through the testnet upgrades. So once we've run more of these shadow forks and that they're consistently stable, we're not finding major issues in any of the clients, and things are generally looking good, then we would move to forking the existing testnets. And the reason we want to be careful with testnets is that today a lot of applications actually use them for production things, even though they're testnets. So for example, Reddit has a big application that's on one of the testnets, and even though there's not like real financial value on them, we'd rather not break those applications if we can avoid it. So once we have these stable shadow forks, we'll move to forking the testnets. And there we have 4 testnets live today. We have Goerli, Sepolia, Ropsten, and Rinkeby. Goerli is probably the most well-known testnet. It has like a super active community, so this is going to be maintained post-merge, and it's a great testing environment because there's a ton of activity on it. Sepolia is a new testnet that we launched. One thing with testnets is like over time they do have a ton of data, kind of like mainnet, and it becomes harder to sync a node. So if they're not super well maintained, it kind of makes sense to periodically just shut them down and create a new one. So Sepolia is our new one, which we hope to maintain kind of longer term post-merge. Ropsten, the Ropsten testnet right now works under proof of work, so it's the only testnet that actually uses proof of work. And because it's a testnet, you get no money when you mine it, so it's a very chaotic proof of work environment. So we'll run it through the merge to just make sure everything looks right, but we'll sunset it sometime after it. And then Rinkeby is an old testnet that's maintained mostly by the Get team, we're not even going to transition that one to proof of stake. We'll do Sepolia instead. So if you are using Rinkeby, you should start looking at other testnets. We're not going to shut it down right after the merge, but at that point, it won't be like a perfect replica of what's on mainnet. And then once we have all these and they're stable and we know it works, then we would move to forking mainnet. So the way it would work there is that we would have to find the terminal total difficulty for mainnet, and it's kind of hard to estimate this because you have to, well, you can set a number, but then you need to figure out how long it's going to take you to hit that number, and because the hash rate varies on mainnet, the farther away your estimation is, the harder it is to get it right. So we're gonna try and have this on the order of like a couple weeks, and the one thing that we can do, so I think some people are probably well aware of the difficulty bomb, which is a thing that happens on mainnet. If this is an issue, we can kind of couple the merge upgrade with the difficulty bomb delay. And then obviously, the number one priority is making sure mainnet stays up, that there's no issues. So if we find an issue with the merge the day before, we would probably delay it because we want to be sure that Ethereum does not go down. It never has, and that's something we're hoping to keep through this. So after the merge, we do have more stuff coming. So the next upgrade we have planned is Shanghai. And there's basically, nothing is set in stone for Shanghai yet, but there's like 3 main themes that we're going to try to get, and then a bunch of small improvements that we're looking at as well. The first big thing is beacon chain withdrawals. So one thing that's worth noting with the merge, because it's like literally the most complex upgrade we've done to Ethereum, we wanted to simplify it as much as possible and cut any excess feature. And one kind of big thing we removed from the merge was the ability to withdraw your stake from the beacon chain. Obviously, a lot of validators have been waiting for this for a long time. So right after the merge, basically the next upgrade, we'll introduce the ability to withdraw from the beacon chain. The second big thing that we're working on is this idea called EVM object format. So everybody wants to improve the EVM, and the challenge we always get when we do it is finding a way to improve the EVM without breaking every contract that's live on mainnet. If we add new functionality, it kind of interacts with contracts that are currently there. If we change functionality, it might change how current contracts behave, and we want to avoid that. So we finally found like a way to do it where we can have a new kind of type of contract that people can use, which the EVM is able to recognize and execute under these different rules. So that's another big initiative that we're working on. The other big one is layer 2 fee reductions. So the kind of really big pressing issue with Ethereum is that the fees are really high. We have layer 2s today which offer lower fees, but if we get another 10 or 100x surge in demand on Ethereum, then the layer 2 fees will be incredibly high as well. So ideally we get a bit ahead of that and we manage to reduce the layer 2 fees. There's 2 different solutions that we're looking at. One is a bit more complicated. One is just a straight up cost reduction, and we're thinking through the trade-offs of both of them. And then finally, there's a bunch of other small EIPs that provide kind of nice features for developers that we're looking to include. All of these are quite small changes. And there's a link to the slides at the end if you want to dive into all of those. And then the last thing I have here is some changes to the process itself. So currently, how we make changes on the execution layer, so like the application layer that people use today to send transactions on Ethereum, is different than how we make changes on the beacon chain. And the reason for that was like when we started developing the beacon chain, we wanted to move a bit quicker, especially because it was a new thing. There wasn't as much at stake on it as there is on the main Ethereum network. So we kind of came up with a different process. But now that we're actually merging both networks together, it would be nice to have kind of a single unified process to propose changes. And neither of the processes we have today are perfect. So on the execution layer side, we use EIPs, which are great to like get the community to know about change and to like specify them in English, but they're not actually like a specification for Ethereum. So the way Ethereum is specified is really weird. We have this yellow paper, which is like a math document that specifies all of the protocol rules. And then we have these EIPs, which are mostly like code or pseudocode, which tell you like, look at the last version of the yellow paper and then make these changes. And they're two documents in like different formats that are pretty unrelated to each other. So it's obviously not great. And then beyond that, we then need to write tests for all these EIPs, and there's no like linking between the yellow paper or the EIPs or the tests. So you basically have humans looking at all of that and making sure it lines up, which is obviously error prone. On the other side, on the consensus layer, we learned from this. So we started with an executable spec. And the idea there is you basically have a Python version of the beacon chain that's implemented. It's not efficient, so like you can't run it like a node, but there is all of the functionality there. So that's, from like a specification point of view, it's really well encapsulated. And it's also really easy to make changes to, because generally the people who propose changes to this are client developers. And so they're usually more engineers than mathematicians, and they can just make a PR against the spec with their change. The thing that is a bit annoying with them is there is no like English or like accessible document to track these changes. So they're usually, scattered throughout the repo of the specs in PRs and comments. And so you can't just say like, this is like EIP 1, 2, 3, 4, and it's a bit harder to like reason about them because of that. But then the last thing is you can generate tests from that spec and you get some better security coverage. So ideally, we'd like to combine both of those two things. There's been work on a project called EALS for Ethereum Execution Layer Specification, which is basically creating a code specification for the execution layer on Ethereum so that we wouldn't have to rely on the yellow paper and EIPs. And there's really a neat way where we could marry these two processes where we could keep using EIPs to specify changes at a high level, give them like a tractable number, have like an English description of like what is this change and why do we want it. But then the actual code specification would be in either the execution layer spec or the consensus layer spec. And another thing we're seeing more and more is features that span both. So for example, beacon chain withdrawals, something has to be withdrawn from the beacon chain and then credited on the execution chain. So having a model like this might be able to allow us to just have a single EIP which says, we're doing withdrawals, here's the execution part, here's the consensus part. That said, it's really easy to speak about this at a high level, like what I do, but actually getting it all to work still has a lot of kinks to figure out. If you're interested in this, there's an active discussion on Ethereum Magicians to contribute to. Oh, okay. That's all I had. I don't know if I have time for questions. I do? Nice. And if you want the slides, the QR code is there.
All right. I'm going to be taking some questions that we got. Okay, one of them is a bit, what if proof-of-work miners start shutting down machines just before the merge in order to prevent ETHDay from being triggered? What do we do then? Yeah,
that's good. So I'll go back to my thing here. Right, so what do you do? Like, we set a terminal total difficulty. Miners are like, well, screw this. I don't want to mine anymore. I'll just stop. And then instead of hitting it in 3 weeks, we're like targeting it to hit it in like 6 months, and the network is not secure anymore. That's really bad. So we have a feature as part of the merge called terminal total difficulty override, which basically allows us to lower the value. So if we were in that spot where like miners stop mining, we simply lower the terminal total difficulty, so we hit it sooner. And the thing that's neat with that too is like, you're always going to run through the merge before the initial value that you set. So like if, instead of hitting it in 2 weeks, we're going to hit it in 4 because miners are dropping off, we can set to another flag, and then anybody who's like not upgraded, there would have been at least a couple weeks where the merge has actually happened, and we can like reach out to those people. So it's not ideal, but I think it works, and we've also tested this on one of the shadow forks, and it worked.
All right. Another question is, I think you covered it, but how are you going to verify the new proof-of-stake protocol will be reliable and not buggy?
So the proof-of-stake protocol doesn't change, and we have a ton of tests for that, and I guess there's two things. One is like, it's been live for over a year with tens of billions in it, and we wanted to wait until we were confident that it was secure before even starting to work on the merge. So a year ago, we were already in a spot where we thought it was safe enough to use. Okay,
actually, one of those questions was asking that. What has the beacon chain been validating exactly all this time since it's launched until the merge?
Yeah, that's a great point. So basically, this diagram shows you and you can't see my clicker, but if you look at like the first beacon chain block, all the stuff there is what it validates. So it's kind of weird. It's just like all the validators are making sure that the other validators are validating, but they're not actually running transactions through the EVM and making sure that those are correct. So you validate, how many new deposits come in, do people get slashed, was this validator the one who should produce the block, and all those things, but you're not actually executing end user transactions.
Okay, one last question, and I think everybody had this question in mind.
I think I'm going to walk off stage.
Thank you for asking it. You must get this like 300 or 1,000 times per day on Twitter. What is the current ETA on the merge?
There is none. Now, I'm not going to say a date.
You're being live streamed.
Soon.
Soon.
Yeah, Trent, if you stay around for Trent's talk after, Trent will tell you at the end of his talk.
That's a nice hot potato. Well, thank you so much, Tim. Thank you so much.
Yeah, thanks, everyone.